Now let's consider sampling a continuous signal. For this system, x of t is a continuous message signal. I'll sketch a function of time. This is the message signal. And let's say it is a continuous signal in time. So x of t is the message signal. We are going to sample this message signal periodically, and we will model that by using the sampling function. This is the sampling function, the sampling signal. It is a summation of time-shifted delta functions. So this is a train of delta functions that occur with sampling period t sub s. So here is a delta function at time t equals 0, and here is a delta function at time t sub s, and the next one is at time 2 t sub s, and periodically this is at 3 t sub s, and at 4 t sub s, and it goes both directions in time. 2, 3, 4. How about that? This is minus t sub s, 1, 2, 3, 4. Okay. So the sampling signal is this periodic train of delta functions, which is mathematically represented by this summation of delta functions. For n equals 0, we get the delta function right in the middle at t equals 0. For n equals plus and minus 1, we get the next two pair of delta functions. For n equals plus and minus 2, we get the next two pair, etc. So we are taking the message signal, multiplying by this train of delta functions, and what results is the sampled function or signal. It's x with the subscript s, so this is the sampled signal. It is simply the product of the continuous message signal and the sampling function, and as we carry that out, we can sketch a graph of what that would look like. Here is the time scale, and I'll pencil in the this is the message signal x of t, and then when we multiply this train of delta functions times this continuous message signal, what we get is a sequence of delta functions, and each of the delta functions is scaled by the value of the continuous message signal. That one looks like it's zeroed out. Here we go. So this is x with the subscript s of t. So these are the time sampled delta functions. The area underneath each one of these delta functions is now scaled by the value of the continuous function. So this one has a scale of x at 0. This one has a scale of x at time ts. This one has a scale of x at 2ts, and this is x, the value at x at 3ts, etc. So this now is the sampled signal. So we've determined what the sampled time signal looks like. Now let's look at the spectrum of this sampled signal. So we've got the continuous message signal x of t into a mixer, a multiplier. X of t goes into this mixer where it is sampled by the sampling function s of t, which is this train of delta functions, and the signal that comes out is the sampled time signal. In the if we look at the spectrum of each one of these signals, see this the sample time signal is equal to x of t times s of t. If we look at the spectrum of the message signal, that would be capital X of f. Let's consider it to have some kind of shape, perhaps some kind of audio signal, and it will have a certain bandwidth b. Okay, so this is the spectrum of the message signal. The spectrum of the sampling signal will be the Fourier transform of this train of delta functions, and I know what that's going to look like. That is going to look like, you take the Fourier transform of the train of delta functions, you get a train of delta functions with a particular scale for each one, and a spacing between the delta functions. So I'll just write it out symbolically as capital S of f, and it's going to be again a train of delta functions. The Fourier transform of the sample time signal using the Fourier transform of the sampled time signal using our multiplication theorem is going to be the Fourier transform of the message signal convolved with the Fourier transform of the sampling function, and this is going to be capital X with the subscript f of f is equal to capital X of f convolved with s of f. So we have, for the spectrum of the sampled signal, first we want to find the Fourier transform of the sampling function. So the Fourier transform of this train of delta functions is fs, that's the sampling frequency or the sampling rate, the number of samples per second, times the summation of delta functions, delta f minus n times fs. Again, we're using the sampling rate. The sampling rate is simply the reciprocal of the sampling period. So the Fourier transform of the sampled signal, capital X sub s of f, is going to be equal to this convolution of x of f convolved with this train of delta functions. Now when you convolve a shape with a train of delta functions, you replicate this shape at the location of each of these delta functions, and we can write that as again a summation n equals minus infinity to infinity capital X, and then we have f minus n times f sub s. I can hear the dogs barking, can you? want to illustrate the spectrum of the sampled signal graphically, which will be a summation of frequency shifted versions of the spectrum of the original message signal. I neglected to put the scale factor f sub s in front, so I've gone back to correct that. Now the message signal has a spectrum that, let's say it has a shape that looks something like this, perhaps some kind of audio signal with bandwidth B, and now we are convolving that shape with a train of delta functions. Each one has a scale factor of f sub s, and the next, this is at 0, and the next one is located at frequency f sub s, and then this is at frequency minus f sub s, and this is a continuous periodic function in frequency of these delta functions. And when we convolve this shape with this train of delta functions, we replicate this shape centered at each one of these delta functions, and what that will result in is a spectrum for the sampled signal that will look something like this. Let's see if I can get something of, here we go. Try to be semi-accurate about this. Okay, this is the spectrum of the sampled signal. What we have is the shape of the original message signal, and it is replicated at centered at 0 is the center copy, and then we have a copy centered at f sub s, and this is at 2 f sub s, and this is minus f sub s, and minus 2 f sub s, and this is periodic in frequency. I've just so it continues, and the message signal has a bandwidth B, so this point is at B, and this point on this side is at minus B, and this center is at f sub s, so this is at fs minus B, this is at fs plus B, and they all have a scale of f sub s. Okay, so this now is what the spectrum of the sampled signal looks like. We have replicas of the spectrum of the message signal centered at multiples of the sampling frequency. The next thing to consider is how to recover the original continuous signal from the sampled signal. And if we look at the spectrum of the sampled signal, we see centered at f equals 0, we have a scaled replica of the spectrum of the original message signal. So we can recover that original message signal by simply use a low-pass filter to recover. What we want to recover is the spectrum of the original message signal. So if we that low-pass filter, let's say, has a transfer function that looks something like this. So this is the transfer function of a low-pass filter, and if we use the transfer function, this low-pass filter, we can recover the spectrum of the original signal. So what we would be doing with the time signal is passing the sampled time signal through a low-pass filter and then recover the original message signal. We know that the transfer function that we wish to use is going to be let's use an ideal low-pass filter with a gain of 1, and it's got a bandwidth that's if it were the minimum bandwidth would be B, so that it would isolate this entire shape. So let's say that this low-pass filter has a transfer function that is equal to the rectangle of f divided by 2 times b. Okay, that would be a rectangle that would fit the spectrum of the original message signal, and we need to use a low-pass filter with this transfer function. Now it's illustrated here as in the time domain. So we have the time signal, the sample time signal into a low-pass filter. What comes out is going to be the input signal convolved with the impulse response. This is the impulse response. And we know that the transfer function is the Fourier transform of the impulse response. So the impulse response has to be the inverse Fourier transform of the transfer function. So we need a low-pass filter. Then the impulse response has got to be the inverse Fourier transform of the transfer function. So that's going to be the inverse Fourier transform of rect of f divided by 2b, which is going to be 2b times the sinc of 2bt, which is the same thing as 2b times the sinc of t divided by 1 over 2b. That's the impulse response for this low-pass filter. Now remember, our input signal is the sampled sample time signal, which is a train of delta functions, each with a different weight. This is the time signal. This would be x sub s of t. And this is going into the low-pass filter, and what is coming out of the low-pass filter is this input string of weighted delta functions, each convolved with this impulse response, which I think this is the, well, let's see what that would look like. What that would look like then, let me draw it down here. This is, again, the time function. We have let's see, I'm trying to get a scale that looks somewhat regular. So when this delta function is input into the low-pass filter, the result is this this sinc function that that would have a certain magnitude given by the magnitude of the delta function. So we would, and then it would, let's see, that would be 1, 2, 3. That's this one here. So, and then okay, so the when this delta function serves as the input to the low pass filter, the output is this scaled shifted sinc function. When the next one serves as the input, we have another scaled shifted sinc function. Then the next one is input that will result in the output being this scaled shifted sinc function. And then when this one is output with scaled negative, and then the next one as well is a shifted sinc function as well. And then this one is this one's positive again. And when you add together the output from each one that results from each one of these shifted input delta functions into this low pass filter that has an impulse response given by the sinc functions, when you add these together, what we get is a reproduction of the original message signal. This is a reproduction of the original message signal, and in the idealized case, it is an exact reproduction of the input message signal. In the frequency domain, we'll look at the spectra of these signals. We've got capital X sub S of F into a low pass filter whose transfer function is a rectangle, an ideal low pass filter, and the output signal is going to be the spectrum of the input signal multiplying the transfer function. So when the spectrum of the input signal is this sequence of replicas of the spectrum of the original message signal. They each have a particular scale. I'm not overly concerned about the scale, because we can always amplify and change scale factors. And now this is going to be multiplied by the transfer function of a low pass filter, and the result of this multiplication is going to be the center replica of this spectrum. So this is X sampled spectrum multiplied by this ideal low pass filter, and it's exactly equal to the spectrum of the original signal, apart from any scale factors. I'm neglecting any scale factors, but we can easily account for scale by amplifying. Then if we take the inverse Fourier transform the inverse Fourier transform of capital X of f, that is going to be an exact copy of the original input message signal. So so what we get is, from passing the sampled message signal through a low-pass filter, is indeed the original message signal is returned. Now remember now that this is all idealized, using as the sampling signal a string of delta functions. So we'll look at more practical cases in a few moments, but this is the idealized system. So we are taking a message signal, an analog message signal, sampling it with this train of delta functions. The question I want to answer now, or address now anyway, is what do we need? What are the limits and the requirements for the sampling period? That will turn out to be a minimum sampling rate. So to find this, let's again sketch the spectrum of the sampled signal. The spectrum of the sampled signal, I'll just it had a copy centered, the copy of the original signal spectrum centered at f equals 0, and it had a bandwidth of b. And then we had the next copy centered at the sampling frequency fs, and it's also got a bandwidth of b. It's got a bandwidth that it goes from this is fs minus b, and this is fs plus b, and we've got another copy for negative frequencies as well. This is at minus fs, and so that's on the frequency scale. So this is the spectrum of the sampled signal. When we change the value of the sampling frequency fs, then this shape will be shifted to the left or to the right. We want to find the minimum sampling rate, or the minimum sampling frequency, so we want to reduce this number until we reach the minimum. For the minimum, we would have it where the right hand edge of this copy just touches the left hand edge of that copy. That would give us the minimum, so that if we are operating with the minimum sampling frequency, this would be fs. Let's see, let me do another one. This would be 2fs. This is at minus fs minus 2. So this is the one we want to be able to isolate this center copy, and we've made if we set fs minus b equal to b, so that these points coincide, then we can solve for the minimum sampling frequency equal to 2b. Okay, so the minimum sampling frequency is twice the bandwidth of the original message signal. So if we know, where did it go? So our original message signal has a certain bandwidth. The minimum sampling rate is twice that frequency. This is the minimum sampling rate, or the minimum sampling frequency, and it is known as the Nyquist, let me spell this correctly, Nyquist sampling rate, named for the person who first demonstrated this. Okay, so the minimum, and this is the minimum sampling rate to accurately reproduce the original message signal. If you have a sampling rate that is lower than twice the bandwidth of the message signal, then there will be overlap in these copies of the spectrum, and the low-pass filter will not recover the spectrum of the original signal, but it will be corrupted by additions from these other copies. That is an effect called aliasing, and we can avoid that by using a sampling rate greater than or equal to the minimum sampling rate. Okay, the sampling we've looked at so far is ideal sampling using a train of delta functions. Well, this is we can work out the mathematics nicely with this. However, in practice, it's hard to get a train of delta functions. What is more practical is to use, instead of a train of delta functions for the sampling, to use a train of rectangular pulses. So if we take a rectangular pulse with overall width tau, and so what that would look like is a rectangular pulse with in time with a width tau, and convolve that with a train of delta functions with sampling period t sub s again, and this is a periodic train. This is in time. See, the result of this convolution will be a train of rectangular pulses that occur. One centered at t equals 0, the next one centered at t sub s and minus t sub s, and again this is periodic in time. Okay, now this is a more practical form of the sampling function. We'll call it s of t again, and now we want to use this rectangular pulse sampling function into a mixer, a multiplier with our continuous signal again. So if I were to sketch what this would look like, what the sampled signal would look like, we have, I'm going to dash in again, this is the continuous message signal x of t, let's say. Might look something like that. Then that will be multiplying a train of rectangle functions that occur every sampling period. So when we multiply this rectangle function by our message signal, what we get is a rectangle, and the top of the rectangle is takes the shape of the message signal and is determined by the value of the message signal, and it's going to look something like this. So this now is the sampled, let me write it this way, x sub s of t. This is the sampled function. It is now it's a train of these thin or narrow rectangles. They have a width of tau, each of them, and the rectangles are now scaled by the value of the message signal, and let me put that there, and here we go, live on screen. Whiteout, how about that? There we go. Isn't that nicer? Now the tops of these rectangles, this is not a flat top. It takes the shape of the message signal at the centered at the location of each one of these rectangles. So now that's the this is the analog pulse sampled version of a sampled signal. Now I want to look at the spectrum of this sampled signal, of this with these natural rectangle tops. They're not flat; they take the shape of the message signal. So if I want to find the spectrum, I'll take the Fourier transform. That will give me capital X of f equal to the Fourier transform of the product of x of t multiplying this sampling function. So that's going to be this is going to be the Fourier transform of x of t, and then for the sampling function, I'm writing this down, we'll have this rectangle, so we're multiplying by the rect of t divided by tau, and that is convolved with a summation n from minus infinity to plus infinity of delta t minus n times the sampling period t sub s. Okay, so I need to find the Fourier transform of these terms. That's going to make capital X, this is a subscript s of f, equal to, see, we've got the Fourier transform of the original time signal. This, when we take the Fourier transform, this multiplication turns into convolution, and then we have the Fourier transform of the rectangle function. And when we take the Fourier transform, this convolution turns into multiplication. So then we have the Fourier transform of this train of delta functions. So that's going to result in capital X of f convolved with the Fourier transform of the rectangle is going to be tau times the sinc of tau times f, and then that's going to be multiplied by the Fourier transform of this train of delta functions is going to be f sub s times the sum from n equals minus infinity to infinity delta f minus n times f sub s. Okay. Yeah. Let's consider this sinc function multiplies this train of delta functions, and then that is convolved with the spectrum of the original message signal. So the spectrum of the original message signal, again, let's take this kind of shape, and then we're going to convolve that with a train of delta functions. Let me sketch out this sinc function, which is going to be that's going to go to a sinc of f divided by 1 over tau. So that looks like a sinc function that has a crossing at 1 over tau and minus 1 over tau, and then this is multiplying this train of delta functions, so it gives a weight to this train of delta functions. And I'll just I'll pick a few here to illustrate. Okay, so the sinc function gives a weight to these individual delta functions. Then when we carry out the convolution, we get a replica of this message signal centered at each one of these delta functions, but now each replica will have a different scale factor. So if I sketch this out below here, it will look something like this. The one centered at f equals 0 is going to be the biggest. Then the one centered at this would be at fs, and this is at minus fs. So the one centered at fs will be the same shape, but it will be scaled to a smaller scale. And this one at minus fs have the same shape, different scale. Okay. Same shape, different scale. Nonetheless, each of these replicas is an exact replica of the spectrum of the original message signal, and provided that the sampling frequency is greater than or equal to twice the bandwidth of the original message signal, we can isolate and filter out the original message signal with a low-pass filter, and again recover the original message signal in its exact form. Okay, the ideal sampling gave us a system that we could analyze mathematically, but it's not very practical to accomplish. The natural top sampling with the rectangular pulses, it's a little bit more complicated mathematically, and it's practical, but it's still not what we wish to use. In practice, what is more often used is flat top sampling. This is what a analog to digital converter will accomplish. We take the message signal again, and we want to model the flat top sampling by sampling the message signal with an ideal train of delta functions, and then taking these delta functions into a pulse forming network that has an impulse response given by this rectangular function. So this is going to be h of t. The impulse response is equal to rect. This is a time shifted rectangle, shifted to 1/2 tau, and it's got an overall width of tau. So for every impulse applied to the input, the output will be this rectangle shape. And if we input scaled impulse functions, then the output will be scaled rectangles. So what we would then have is, let me illustrate the sampled signal. Here is the message signal again. This is our continuous message signal x of t. The sampling signal will sample with impulse functions that occur periodically. And so when the sampling occurs, we get a delta function that is scaled by the value of the message signal at that instant, and then this delta function serves as the input to this pulse forming network, which causes the output to be a rectangle with a flat top that continues for a period of time equal to tau. So this would be minus t sub s, 2 times t sub s, in this case, is the sampling time, and it produces a rectangle with a width of tau. And then the next sampling produces this small rectangle, and then this is at time t equals 0. The sampling produces a rectangle that's negative again, and then this is at time t sub s. That produces a rectangle. Now all of these rectangles have a flat top, and this now is the form of this is the sampled function that comes out of the pulse forming network. This is now flat top sampling. These are all flat tops. This is the result we will get with an analog to digital converter that samples the signal at an instant in time and then converts that value to a constant. So now we want to look at the spectrum of this flat top sampled signal. So let me write down the equation for this time signal. This is going to be input, which is x of t, that's multiplying our sampling signal, which is a train of delta functions, with sampling period t sub s, and that is now this train of impulse functions is the input to this pulse forming network, and so the output is going to be the input convolved with the impulse response, which is rect of t minus tau over 2 divided by tau. So when we take the Fourier transform, of this equation, we'll get capital X sub s of f is going to be the Fourier transform of x of t, so that's just x of f. This multiplication turns into a convolution, and we have the Fourier transform of this train of delta functions, t minus n times capital T sub s. And then this convolution turns into a multiplication with the Fourier transform of this rectangle, t minus tau over 2 divided by tau. Okay, so this is going to be Fourier transform of the original message signal convolved with, and now we've got the Fourier transform of this train of delta functions, which is going to be fs times the sum from n equals minus infinity to plus infinity delta f minus n times fs. And then that is multiplied by the Fourier transform of this rectangle. So this has a time shift, so we get an e to the minus j 2 pi f times tau over 2. Then we get from the Fourier transform of the rectangle a tau times the sinc of tau times f. We can group the spectrum of the original message signal convolved with this string of delta functions. We can make this the first term. Then we can multiply the result of this convolution by e to the minus j, let's call this pi f times tau, and then that's multiplying tau sinc, and then we have an f divided by 1 over tau. And when we sketch this out, what we have first of all, we've got this the replica of the original message signal that would look something like this. Okay, this is the result of this convolution. We get exact replicas of the message signal. This is at f equals 0. This is at fs, and this is at minus fs, and this is periodic. And now we're see this is the result of this convolution. Gives us replicas of the spectrum of the original message signal replicated at the multiple values of the sampling frequency. Then all of this is multiplied by a sinc function. Let's disregard this complex exponential. This will give a phase angle. This has a magnitude of 1, and it will give a phase angle that. So I'll just show the magnitude. And again, I'm not overly worried about the scale factors. I'm more worried about the shapes of these functions. So we're going to multiply this with a sinc function that looks something like this. Let's say this is make it like this. This is the magnitude of e to the minus j pi f times the sinc of f divided by 1 over tau. Okay, if we look at the magnitude of that, it would look something like this. Again, I'm neglecting the scale factors because I'm not overly concerned about the scale factors. Anyway, this would have a crossing at 1 over tau and minus 1 over tau. So, so when we multiply these two together, when we multiply these the replicas of these shapes times this sinc function, what we get is we get a spectrum for the sampled signal where I'm going to draw it like this to illustrate. This is capital X sub S of F for the flat top sampling. This center copy, this is multiplied by a pretty flat, relatively flat region, but it does drop off a little bit toward the edges. So there is in this center replica, there is some distortion to this replica, but it's not as bad as over here when this shape is multiplied by this this more pronounced sloping line. So this would be more distortion, but that really doesn't concern us too much, because again we're going to use a low-pass filter and because we know the characteristics of this pulse forming network, and we can then, it is possible to see in this case it tends to de-emphasize the higher frequencies. So it would be possible then to take this sampled, flat top sampled signal, low pass filter, and then compensate for this distortion with another filter, and achieve good results. So so we're going to take the sampled signal into a low pass filter, and then a compensation filter, which would be essentially a high pass filter of some kind, compensation filter. But it's conceivably we could match the compensation filter closely to the characteristics of this pulse forming network, and cancel the effects and retrieve the original signal back again. Okay, so this is the results with flat top sampling. Okay, in practice, we don't want to just sample at the minimum sampling rate, which is the Nyquist rate. So see, we have our continuous message signal, which has a spectrum that looks something like this, let's say, with a bandwidth of B, and we're taking this into a sample and hold circuit that will be controlled by a clock with a certain sampling frequency, and what comes out of the sample and hold circuit is our sampled signal. Now the spectrum of the sampled signal, if this is for the sampling frequency exactly equal to the Nyquist rate, which is 2B, the Nyquist rate. Okay, so then if we sample at the minimum sampling frequency, we get replicas of the signal spectrum. This would be at Fs. This is periodic in time, or in frequency, I'm sorry, and this is at minus Fs. Now this is the minimum sampling rate. It's more likely in practice that we would want to sample at a frequency that is higher than the minimum, so that the spectrum of the sampled signal looks more like this. This is Fs. This is that is B right there. So this is B. This is Fs minus B. This is for the sampling rate greater than the Nyquist rate. And the good thing about this is we now have room in the frequency space for practical low-pass filters. The ideal low-pass filter simply cannot be built, so it is not practical in use. So for audio, for good audio, the bandwidth is going to be about 15 kilohertz. So the Nyquist rate is going to be equal to two times the bandwidth, so that's going to be equal to 30 kilohertz. So for good audio, this is CD quality audio or better. The Nyquist rate, the sampling rate, has to be 30,000 samples per second. In practice, for compact disc audio, you remember compact discs, don't you? If some of you may still have one. The sampling rate is, I think, I'm going from memory, I believe it's 44.1 kilohertz. 44.1 kilohertz. That's the industry standard. Before we leave sampling, let me discuss another issue. With most message signals, like an audio signal, whatever the spectrum of the audio signal looks like, it does not have a sharp edge for a bandwidth. It kind of the frequency components kind of tail off toward zero, so sometimes it's hard to define a sharp edge. So if you sample this signal at some sampling rate, what you will then potentially find is that there will be some overlap toward the edges of the low pass, the band of the edge of the low pass filter, and this will cause the recovered signal to be distorted. Now this effect, where we have overlap at the edges of the replicas of this spectrum, this is called aliasing, and it causes potentially distortion in the recovered signal. Now, to address this problem, what is often used is an anti-aliasing filter. The anti-aliasing filter will have, see, this will have a transfer function that is going to be essentially a low-pass filter that will have a very sharp cutoff, or as sharp as you can reasonably build. So this has a sharp cutoff, so that the signal that is then applied to the sampling circuit has a more definite cutoff frequency. Let's see, this is the spectrum of the signal that's going into the mixer. See, it gives the message signal a sharp band cutoff, a sharp bandwidth, band limit. I'll write it that way. Okay. Now, so you can argue, and I guess conceivably argue very well, that you're going to be intentionally losing some of this high frequency, some of the high frequency components. Yes, that is true, but at least you're losing them in a controlled fashion, rather than getting distortion in a more uncontrolled fashion. So it is very common to take the message signal into an anti-aliasing filter. This is a low-pass filter that gives the message signal a sharp cutoff, and then that signal is sampled and converted. In the case of an analog to digital converter, it is converted to a digital signal. Sampling a signal also gives us an opportunity to use a common channel and transmit more than one signal using time division multiplexing. I've reduced it down to two input signals, X1 and X2, and we can apply each of these input signals, message signals, to a sample and hold circuit, and have the sample and hold circuit controlled by a two-phase clock. Signal would normally be a square wave. Then we could have one of the sample and hold circuits that is triggered on the rising edge, and the other sample and hold circuit triggered on the falling edge. So this one is triggered on the falling edge. So if I sketch the message signal, well, let me sketch. Yes, I'll sketch the message signal. This is here's message signal number 1, and I'll use a different color for message signal number 2. So the blue is X1 of t, the red is X2 of t, and then we've got a clock signal that, let's see, it would be something like this. This is the clock. So that the sampled signals that are added together would look something like this. Let's see, the X1 is sampled on the rising edge. So on this rising edge we get a sampled signal that looks something like this, and then this next rising edge, it's smaller, and then on this rising edge it looks like it's a little bit negative, and on this rising edge it's still negative and it's even larger, and on this rising edge it looks like this, and on this rising edge it's a tiny little signal like that, and on this rising edge it's back positive again. Okay, so that's signal X1 that is sampled on the rising edge of the clock. Then on the falling edge of the clock we sample the other signal. It's a falling edge. It still looks something like this. Here's a falling edge, and we have a signal there, and this falling edge, it's here, and this falling edge, it's a negative value. So you can see this is we've got two signals on the same transmission line, but they are divided. Time is divided into two different frames. This is time division multiplexing, and it allows for sampled signals to be transmitted on a common transmission line. I grant you it's not much of an advantage with just two signals, but if you could imagine 8 or 16 signals multiplexed together, you could then that could be quite an advantage perhaps. Okay, one last topic dealing with digital communication systems. Those are the systems we're leading to. We have a message signal X of t. This message signal has a spectrum, capital X of f, that has some kind of shape, and it has a bandwidth b. This is the bandwidth of the message signal. We're taking this message signal into a sampling circuit, and the sampling circuit is controlled by a clock that is running at a frequency which is I'll call it SR for the sampling rate. So this clock controls the sampling circuit. The clock is running at a sampling rate, sampling our continuous input signal at a particular number of samples per second. The sampled signal is then applied to I'm going to call it a digitizer. The digitizer turns these samples into a digital number, converts the sample values into a binary. I'm going to call it a binary number with n bits per sample. And what comes out of the digitizer is a string of digits, of ones and zeros. So the string of ones and zeros come out of the digitizer at a certain bit rate in bits per second. So bit rate BR. The bit rate is equal to the sampling rate times N. See, the sampling rate is in samples per second, and N tells you the number of number of samples, number of bits. N tells you the number of bits per sample. So when you multiply the two together, you get the number of bits per second. Okay, so the bit rate for this digital signal is dependent upon two things: the sampling rate, that's the number of samples per second, and then the number of bits used per sample. So the bit rate is the sampling rate times the number of bits per sample, and the sampling rate for reconstructing the signal from this digital representation of the signal, the sampling rate has got to be greater than or equal to twice the bandwidth of the original message signal. Okay, so we start with an analog signal with a certain bandwidth. Based on that bandwidth, we can come up with a sampling rate, and then those sampled signals are turned into a binary number with a certain number of bits per sample, and we will talk in the next section about the limits and the requirements for that number of bits per sample. And the result is a digital signal. This is a digital signal, or I should say perhaps a binary signal, which is simply a string of ones and zeros that have a certain number of bits per second. Okay.
Let's all go to the lobby. Let's all go to the lobby. Let's all go to the lobby to get ourselves a treat.
Delicious things to eat.
The popcorn can't be beat. The sparkling drinks are just dandy. The chocolate bars and the candy. So let's all go to the lobby to get ourselves a treat. Let's all go to the lobby to get ourselves a treat.